Hello. Today I would like to talk about transformer regulation, especially for load flow calculation. To do this, I used my toolboxes in LSpice to draw a circuit with a 400-volt voltage source, a small series impedance, and two parallel transformers with external control of voltage level and voltage angle. For simplicity, both the primary and secondary sides of the transformer are at the same voltage level of 400 volts. The transformers also have no internal resistance and no losses or magnetizing currents. The two transformers also have internal control, but due to a slightly different implementation, the transformers of the load flow toolbox and the transient toolbox can only be simulated accurately with external transformer control for comparison purposes. There are two different transformer controls: control of voltage level, longitudinal control, and control of voltage phase, i.e. diagonal or quadrature control. In longitudinal control, i.e. voltage level, either additional or a reduced number of turns of the same winding are connected. In 60 and 120 degrees diagonal phase control, turns of one winding are added or removed from another winding. In 90 degrees phase, i.e. quadrature, control, turns of the other two windings are added or removed from one winding. Longitudinal regulation controls the voltage level, while diagonal or quadrature regulation primarily influences the voltage phase. There is also a regulation, the diagonal control, which is a bit of both. Longitudinal regulation influences the reactive power via the transformer, while quadrature or diagonal regulation primarily influences the active power. Reactive power always flows from the higher to the lower voltage, while active power flows from the higher to the lower phase angle. As we will show later, the above only applies because the transformer impedance is primarily inductive. If the transformer impedance were only ohmic, the effects of longitudinal and quadrature or diagonal regulation would be reversed. The different controls are shown schematically in the circuit diagram at the bottom right. The external LTSpice transformer control models are called Trafo-Tap-L for longitudinal control, Trafo-Tap-Q for transverse control, and Trafo-Tap-S for cross-regulation of both at the same time. The two transformer control block symbols are called Tap1Q and Tap2Q. For an initial simulation with transverse regulation, I set the Q parameter of the Tap1Q element to +10. The Q parameter of Tap2Q remains 0. Then I start the simulation. Now I plot the active power flow at pin PTR1A of transformer 1. The value is approximately 6.2 kilowatts in the direction of the input pin. Note, the two outer pins are the active power pin PTR1A into the input pin and the active pin PR1B into the output pin. The next inner pair is the reactive power, and in the middle are the two voltages, primary and secondary. Briefly about the measured values as a result of the simulation. The output is always in volts. However, the unit can be changed by multiplication. To output a power value, multiply the value of 6.2 kilovolts 1 watt per 1 volt to obtain 6.2 kilowatts. Now we plot the active power flow at the input of transformer 2, pin TR2A. The value is 6.2 kilowatts. The negative sign indicates that the active power flows out of the input pin. We therefore obtain a circular flow of active power via transformer 1 to transformer 2. If transformer 2 were loaded in the forward direction, it would now be unloaded by the control of transformer 1. This is exactly the task of phase regulation, some reducing of loading of lines or transformers. Hint: active power always flows from the higher to the lower voltage angle. With transformer control in the neutral position, Q equals 0, the voltage angle is approximately 0 degrees on both the high voltage side and the low voltage side, as well as in the middle at bus 12, and the active power is 0. Both transformers are completely unloaded. At Q equals 10, the voltage angle at bus 12 is minus 2.8 degrees, and at bus 2, plus 2.8 degrees. The total angle across the transformer regulator is 5.6 degrees. The active power flows from 0 degrees at bus 1 via transformer 1 to minus 2.8 degrees, then via transformer 2 from 2.8 degrees back to 0 degrees. Now, just briefly for comparison, the same circuit with the transient toolbox. We again have our voltage source, the two transformers, and the external transformer controls. In front of the transformers are the measurements for the active power. I will now start the simulation. As we can see, the active power flow is 6.2 megawatts from transformer 1 to transformer 2. If transformer 2 were heavily loaded by a load on the bus bar, it would now be relieved. The voltage angle is approximately 2.9 degrees, as in the previous simulation with the load flow toolbox. The simulation is much better here with the load flow toolbox, because many measured values can be called up immediately. Now let's simplify the circuit even further. The transformer is replaced by an impedance. To obtain this value, you must insert .options log params. Then start the simulation. After the simulation, use View Spice log file to search for the variable Trafo1x codes. This has the value XL of 1.28 ohms. Now we have everything we need to simulate the circuit with the impedance instead of the transformer. We now open the file, 2 transformers QTAP XK to AS key. We now start the simulation. Now I plot the active power flow at pin PTR1A of transformer 1 again. The value is approximately 6.2 kilowatts in the direction of the input pin. Now we plot the active power flow at the input of transformer 2 pin TR2A again. The value is minus 6.2 kilowatts. The negative sign indicates that the active power flows out of the input pin. We thus obtain a circular flow of active power with the same values as in the previous example. As can be seen in the example, the voltage across the TAP1Q element is approximately 40 volts. This value is calculated by multiplying the nominal voltage of the circuit by Q and ST-pros percentage, divided by 100 equals a 400 volts to 10 100 equals 40 volts. This value can also be measured directly in the circuit because the value is purely imaginary, and the differential voltage at the element can be measured at its imaginary pins. The differential voltage is approximately 23 volts. Multiplied by the square root of 3, this results in 40 volts. Now I measure PMP at the impedance of the source. The value is negligible. This means that the active power flow only flows between the transformers in the circuit but does not flow back to the source. This allows me to simplify the circuit even further. I now replace the transformer controls with fixed voltage sources and combine the 400 volt voltage source with the voltage sources for the transformer controls. The series resistance after the voltage source is removed. Now I open the final greatly simplified circuit with quadrature control called 2 transformers QTAP SXK simplified. We will also use this later to simulate the longitudinal control. The diagonal control is a mixture of both and will only be discussed briefly as it does not provide us with any new insights. Now we are ready for the further simplified circuit. We see 2 voltage sources as replacements for the transformer control and the 400 volt voltage source, and 2 impedances as replacements for the transformers. The upper voltage source is now set to VR equals 400 volts and VI 40 volts. This is the setting for Q equals 10. The lower voltage source is at VR equals 400 volts and VI equals 0 volts. This setting is for Q0. We see now to the active power flow at pin PTR1A of transformer 1 and pin PTR2A of transformer 2, and obtain 6.2 kilowatts and minus 6.2 kilowatts. So again, there is a circular flow from transformer 1 to transformer 2. The voltage angle at bus 4 after the voltage source tap 1 is 5.71 degrees. The voltage angle at bus 5 is 2.86 degrees, and at bus 6 it is 0. The active power always flows from the higher angle to the lower angle. That means from bus 4 to bus 5 to bus 6. The voltage is 402 volts in bus 4, 400.5 volts in bus 5, and 400 volts in bus 6. The current is purely real with 9A, voltage imaginary, impedance imaginary, current real. The reactive power always flows from the higher voltage to the lower voltage. This can be seen by plotting the sequence Q transformer 1A minus Q transformer 1B minus C minus Q transformer 2B and Q transformer 2A. The voltage source tap 1 first supplies 625 var to transformer 1 where 3L.5 var is consumed, and the remaining 312.5 VAR is supplied to transformer 2 and consumed there. We now set tap 1 to VR 400 volts and VI at minus 40 volts. This is the setting for Q minus 10. We see now to the active power flow at pin PTR1A of transformer 1 and pin PTR2A of transformer 2 and obtain minus 6.2 kilowatts and 6.2 kilowatts. This means that the circular power flow is now in the other direction, from transformer 2 to transformer 1. We now set tap 2 to the same value as tap 1 at Q equals 10 with VR equal 400 volts and VI equal 40 volts. We start the simulation. The active power flow through the transformers is now 0. The same applies to the reactive power flow. The current is therefore also 0. The voltage at the slack bus 4 is now exactly the same as the voltage in bus 5 and bus 6, since no current results in no voltage drop across the two transformers. The voltage angle in bus 5 now has its highest value, namely 5.7 degrees, which is twice as high as in the previous example and would result in a high active power flow to the other grid when coupling bus 5 with another grid with a small voltage angle. We will now explore the case where tap 2 is set to Q equals minus 10. We can now see that the active power flow of 12.5 kilowatts is twice as high as in the first example. The current IR is also twice as high at 18A and again purely ohmic. The voltage angle in bus 5 is now 0. The voltage angle in bus 4 is 5.7 degrees and the voltage angle in bus 6 is now minus 5.7 degrees. The active power flows from the higher to the lower voltage angle. So from bus 4 with 5.7 degrees to bus 5 with 0 degrees to bus 6 with minus 5.7 degrees. The small reactive power flows from tap 1 to transformer 1 where it is consumed, and from tap 2 to transformer 2 where it is consumed. The reactive power requirement of the transformers is now 4 times as high, namely 1,250 kilovar. This is due to the higher current depth flowing through the transformers. The requirement is proportional to I squared. Since I is twice as high, Q is 4 times as high. It can be seen that the reactive power demand can become very high in a transformer with high inductance. In a 300 megavolt ampere transformer, the reactive power demand at full load is in the order of 50 megavars, and in the event of a short circuit, much higher, far exceeding the rated power of the transformer. We will now look at the longitudinal control of a transformer. To simulate the longitudinal control with tap 1 of L equals 10, tap 2 L equals 0, the voltage source tap 1 is now set to VR equals 360 VI equals 0. The simulation is now started. The reactive power at the input of transformer 2 equals 6,250 kilovar, at the output 5,937 kilovar, at the output of transformer 1 5 by 937 kilovar, and at the input 5 and 625 kilovar. This means that the reactive power from transformer 2 flows through transformer 1 in a circuit. It flows from the higher voltage to the lower voltage. 400 volts from tap 2 to 380 volts in bus 5 to 360 volts in bus 4. You can see that the voltage level in bus 5 has now changed significantly. The voltage angle is approximately 0 and remains 0 during the simulation of the longitudinal control for all bus bars. The current is purely imaginary at 9A, voltage real, impedance imaginary, current imaginary. Now I set the tap 2 controller to L equals 10. This means VR 44360 V0. I start the simulation. The reactive power flow through the transformers is now 0. The voltage in bus 5 now has the same value as that of the voltage sources, namely 360 VU. This is logical because the currents through the transformers become 0, and therefore there is no voltage drop across the transformers. Now I set the tap 2 controller to L equals 10, tap 1 L equals 10. This means VR equals 400 plus 40, 440 volts, VI equals 0. I start the simulation. The reactive power flow through the transformers is now twice as high as in example 1. The voltage in bus 5 now has the same average value as the two voltage sources, namely 400 volts. At 18A, the current is twice as high as in example 1 of longitudinal control. Now for a quick test, I changed the transformer impedance by setting it to purely ohmic R equals 1.28, XL equals 1e⁻⁶. Now I start the simulation again. As you can see, the longitudinal control now behaves like the quadrature control. Instead of shifting reactive power via the transformers, active power is now shifted. This means that longitudinal and quadrature control only work because the transformer impedance is largely imaginary. With minor 120 degrees, 60 degrees oblique control, longitudinal and oblique control are mixed. The proportion of longitudinal control is half 0.5, that of oblique control 0.86I. The magnitude of both together is 1. S=10 means 40 volt 0.5 plus 40 volt 0.866I for the additional voltage. When simulating oblique control, our simplified model becomes inaccurate. However, you can see how the skew control works in qualitative terms. I hope you enjoyed this brief introduction to longitudinal and quadrature control. Goodbye.